Hi everyone, our project is titled Reinforcement Learning for Optimal Sequential Decision Making for Cyber Threat Mitigation. It was done by me and Brian. In 2017, Verizon and SANS reported that 68% of attacks went undiscovered, and even after detection, 77% of these attacks took hours to days to get mitigated. The automation of threat mitigation is particularly important to make real-time decisions against cyber attacks. Our goal is to develop an automated decision-making agent using reinforcement learning to observe and respond to cyber intrusions accurately and timely. So in some related work, they had developed a multi-agent POMDP, which has been used only for dynamic defense of vulnerable large-scale cyber networks. Our task is to expand this and develop a single defense agent that will dynamically mitigate any kind of adversarial action using any system or network using the MITRE ATT&CK framework. The MITRE ATT&CK framework is structured in tactics and techniques. The categories are the tactics up top, and within each tactic are techniques. Every technique has a mitigation. A technique that's been used, or highlighted in yellow, is composed in an attack chain, and that's an instance. In total, there are 266 attack techniques, 41 mitigations, and 300 real-life attack instances. In our problem formalization, we define the states to be our techniques, the actions to be the corresponding mitigations, and the set of observations as the commands or the traces of the techniques. We also have the transition functions, observation function, reward, and discount factor as normal. Our approach has 4 steps. First, a preliminary POMDP approach with a constrained attack graph, then a Q-learning of real-life attack data, third, attack data generation using RNNs, and then a deep Q-learning of real and generated attack data. In order to account for all the states, in our case techniques, and all the different complex attack paths, we chose to perform Q-learning, which is just a model-free reinforcement learning algorithm. The formula for that you could see is below. We lacked the partial observability constraint in our POMDP model, and we saw that with the regular Q-learning on the real-life 300 attack dataset, it wasn't complex enough and it easily learned all the optimal policies. So we decided to generate more attacks. Similar to a text generation approach, we had the beginning of our attack chain tokenized. That was fed into an embedding layer, 3 LSTM layers, and a linear layer, and that gave us the completed new generated attack chains. We were able to generate around 1,000 new attack instances. That allowed us to do deep Q-learning.
Hi, so my name is Brian, and I'll be talking about how we implemented the Q-learning and the deep Q-learning network. So in order to do this, we basically translated our full data set, the mitigations, and the techniques, and then created a table based on how they interact with each other. From this, we set up simulations of games that randomly pick from real and generated attack sequences, and then we create rewards based on the stage or each technique. In addition to that, our goal is to predict and mitigate the next state in an attack sequence. So from there, with our Q-learning, we use the Q-learning algorithm to update that part. And with a deep Q-learning network, what we did was we implemented it like this. We had a 2 linear layer network with an embedding layer, and we're passing it through with replay memory and a local and target network to stabilize the results. So the results of that are that we see that there are positive rewards for using the deep Q-learning network, and the baseline, which is the green and the yellow line using random choice and the most common mitigation tactic, are that they are about the same as regular Q-learning. So we can also compare the win rates for each of these, and we can see that deep Q-learning beats out every other tactic, where Q-learning still does pretty well. Now there's a concern that we're overfitting the data because there's not much, but we can see that before we even reach all the data, we're already learning a lot, and so we can be pretty sure that this generalizes. In addition to this, we can interpret the Q table here. So to pick the optimal policy, what we can do is we can go to each technique or each state and find the highest reward. This then corresponds to our optimal policy, and if we count how many mitigations are used for both the Q-learning and deep Q-learning network, we can see that using Q-learning, it's pretty uniform. But if we move to deep Q-learning, it actually picks the mitigation tactics that cover the most states. So it's not generalizing to one mitigation tactic, but the most powerful mitigation tactics, and that's what we can interpret from this data.
In conclusion, we developed a reinforcement learning agent to observe and defend against cyber threats optimally in real time. We learned and generated attack chains using recurrent neural networks, and we also developed a deep Q learning to mitigate attack techniques. Within that, we used replay memory. We took the actions based on the predicted next technique, which allows for automation of cyber defense and being ahead of the adversary. And our deep Q learning approach, optimal policy rewards exceeded that of the baseline and Q learning.